Yeah. So good afternoon, everyone. And for those of you who are joining from Europe, also good morning for those of you from America, as well as good evening for those of you from Asia. Welcome again to the joint IFAC IEEE CSS webinar series on nonlinear control systems, which is organized by two technical committees, the one from IFAC as well as from IEEE. And this is organized by various different people. So I would like to thank as well to Christophe Prieur, also Claudio Califano, and Andrea Serrani. So today we have the pleasure of welcoming Professor Rodolphe Sepulchre, who is just moving to KU Leuven recently, but he is also still maintaining relations with Cambridge. He's going to present talk about nonlinear feedback analysis, back to the future. So it's going to be a very interesting topic that he's going to tell us. But briefly about this is about it's not about Frank Algauer. That is a bit of wrong in the name. I'm sorry about that, Rodolphe, but the rest is still correct. So Rodolphe is a professor in the Department of Electrical Engineering, KU Leuven, Belgium. His research interests are in dynamics control and optimizations of nonlinear problems. And he's currently the editor-in-chief of Systems and Control Letters and has been associate editor for SIAM, Journal of Control and Optimizations, Journal of Nonlinear Science, as well as Mathematics for Control Signals and Systems. He was awarded the IEEE Control System Society Antonio Ruberti Young Researchers Prize. He's also fellow of IEEE and SIAM, and he has been the IEEE CSS Distinguished Lecturer between 2010 to 2015. He is also currently working on the ERC Advanced Grant on Switchlets, which is motivated by neurophysiological questions and aiming at multi-resolution control theory of excitable systems. He has written a number of books, and I think it's time for us to welcome Rodolphe. And before that, sorry, Rodolphe, I would like to again announce that we are going to have the next speaker. I'm going to announce it now that it's going to be Professor Arjen van der Schaft from Bernoulli Institute for Mathematics, Computer Science, and Artificial Intelligence, as well as affiliated to Jan C. Willems Center for Systems and Control from University of Groningen. He's going to talk about Pot-Hamilton systems theory and monotonicity, so please reserve this in your agenda. Now, I think without any further ado, I'd like to give the floor to Rodolphe. And again, Rodolphe, apology for a mistake in the name, and I'd like to give the floor to you. Rodolphe?
Yeah, thank you. I suppose I should take this as a great honor. Okay. Hello, everyone. A pleasure to be given the opportunity to speak in this webinar. Before I start, I'd like to, sorry, this is not working. Yeah. That's better. So I'd like to acknowledge that this is joint work with three colleagues. So Tom Shafi just finished a PhD with me in Cambridge, as is now a postdoc there. Henk van Waarde did a postdoc with me some time ago and is now an assistant professor at the University of Groningen. And Fulvio Forni is a long-time collaborator in Cambridge. The topic of my talk today will be, and before I proceed, of course, I will very much welcome your questions, and I hope we can have some discussion at the end of the talk. So please use the chat to write your questions, and I will read them at the end of the talk. The topic of my talk will be is a most classical topic, I would say, the feedback analysis of nonlinear systems. And it will be somewhat high level in the sense that I will not spend much time on the technical details. I will provide you with some pointers to the technical details, but instead I will spend time on, I hope, very simple examples that I hope will illustrate the point that I wish to make. And I would like to start this presentation with a short discussion of those two examples. So the first example is not from my research, but is a fairly classical problem where, and it's what I would call a very mindly nonlinear feedback system, in the sense that the plant is modeled as a linear time invariant system. And the controller is also very elementary in the sense that it's a classical PI control. So, and integral action is there because you want steady state performance. And of course, we know that this comes with a price, that an integrator also introduced a phase lag of 90 degrees, and that is not so good for the stability margins of the system. And from very early on in control, the proposals were made, particularly by this paper by Clegg, to implement the PI controller with a slight reset mechanism that reset the integral action to 0 whenever there is a mismatch between the error, the sign of the error and the sign of the input. And the claim was that perhaps with this modification that makes now the controller nonlinear, perhaps you can overcome this trade-off between 0 steady state error but degraded stability margin, or at least you could alleviate the phase lag of the linear integrator. And there has been a resurgence of interest for this type of nonlinear mechanism that is part of the controller. So it's here we have a nonlinearity that is designed for a performance purpose, and the topic has known a resurgence of interest because it's an example of hybrid system, and so it is a very good example to see whether the theory of hybrid systems can provide new insight on this classical and old question. But I would say that I find this somewhat humbling that nowadays what we can say about the robust performance of this feedback system is not that different from what we were able to say in 1960. In the sense that most of the insight that we have on such a system still comes from perhaps approximating the nonlinearity with the describing function and then using classical tools from the frequency domain and classical control. And in fact, if you want I think a very good illustration of that, I would recommend the plenary talk of Marcel Hertjes at ECC a year ago. I have visited Marcel recently, and it's very impressive to see how this nonlinear type of integral control can, the impact that those controllers have in high performance motion control. Those applications are for machines that design or chips and wafers. So it's a very, it's really the state of the art of what we can do with motion control. And what I found very interesting in his plenary talk, which is excellent, by the way, is that the first half of the plenary talk is really about the insight and the design that you gain from this describing function analysis and the classical frequency domain analysis. And then in the second part of the talk, this is sort of contrasted with the difficulty of coming up with a sort of a more comprehensive analysis of the states with guarantees for the state feedback system. And the difficulty of analyzing this. And he's really making a call in his talk for new and rigorous robust performance analysis for such nonlinear systems. So this will be my first example. Now, the second example comes from something that is very much closer to my research. And this is about studying the robust performance of an electrical circuit that comes from the work of Hodgkin and Huxley, and that is somehow the foundation of quantitative neuroscience. So that model was derived to model the excitability of biological neurons. And this is not going to be the topic of my talk today, but I extracted from this model. So this circuit is made of one capacitor and then a parallel interconnection of current sources. And each of those current sources has a model that's very much resemble the state space model that I have extracted here, which would model what I will call the potassium current, which is one of those branches. And if you look at the state space model of this potassium current, you recognize a static relation between current and voltage. So it's essentially a resistor, but the conductance of that resistor is state dependent, and the state models a lag, a nonlinear lag, if you wish, of the voltage. So you can really think about this current source as a resistor, but that is sometimes called a memoristic element because the resistance has a form of memory. So you can think of it as a lagged nonlinear resistor, but it's still an extremely simple model and very physical model of a nonlinear device. And I will argue during the talk that even about such a simple input-output one-port circuit, we can say very little in terms of characterizing the input-output performance. And the reason why I've developed a lot of interest in those simple models is related to my interest for neuroscience, but that also stems from the fact that this is an area of biology where we have circuits, and we would think that, you know, it's difficult to be closer to control theory than starting from circuit models. This is where we see the foundation of control theory and the foundation of all the important concepts of nonlinear control theory. And so also there, I find it very humbling that we can say so little about the performance analysis of those feedback systems. And I think that there is a strong interest nowadays to develop new design and analysis tools for these nonlinear circuits, because they don't only appear in neuroscience, but also in neuroengineering. And more recently, you can hear a lot about neuromorphic engineering and neuromorphic computing. So the idea of mimicking those devices in hardware. And I think we have a whole community there waiting for better analysis and design tools. So those will be the two examples, the two running examples of my talk. And now, as the first part of the talk, I'd like to share with you what I mean by the gap between the input-output properties of those devices and the very simple state space representation that they have. So if we go back to the very early days of feedback analysis, which I put here an excerpt of the PhD dissertation of George James in 1960. And so at the onset, the view of George James was that we should think of a system as an input-output operator, mapping signals to signals, and that we should study the performance of feedback systems by studying incremental input-output properties. And here you have a definition from James' dissertation about the incremental gain of this system, this operator H. And it is defined as X and Y are two input signals, and H of X and H of Y are the two corresponding outputs. And so you measure, when you go from one signal to the other, the difference, how much this difference can be amplified by the system. So this is sort of the worst gain amplification, but what I want to insist on is that it is an incremental quantity. So if you think of H as a static function, this characterizes the gain of the slope of that function. So it is an incremental quantity. It's not the absolute gain of the function. And the point that I want to make today, and that I illustrate on the two examples that I have discussed, is that we don't really have a methodology to analyze incremental input-output properties when we start from nonlinear state space model. We have very few worked out examples where we can compute those quantities. And if you open the textbooks of nonlinear control today, there is very little about those incremental quantities. And I'd like to contrast the very start of nonlinear theory with the theory of George James and what happened and what made it the current theory has sort of moved away from that approach. And I would like to contrast the input-output theory that was very popular in the 60s and still 70s. And then from the late 70s and early 80s, we have seen the introduction of state space models in nonlinear control. And that is now, this is where you see the most emphasis in all the nonlinear control textbook. Of course, we know that the input-output theory is sort of grounded in circuit theory that has, I would say, very much disappeared from nonlinear control. And in contrast, I would say that the state space theory is very much grounded in mechanics, but there the focus is on non-incremental properties. So that will be the theme of the talk, and I'll try to contrast those two and to talk about the difficulty of matching the two. And in order to do that, I will very briefly summarize what we can find in the latest, I think, input-output textbooks, the very famous textbooks of Vidyasagar and de Zoor in 1975. And there you have this concept of passivity that comes from circuits, which is an operator theoretic concept. So you think of the system as an operator on a signal space, so it maps U and Y are signals, typically in L2, and you consider the inner product of those two signals in L2, so the integral of their product over time, and that quantity, if that quantity is positive for every signals, then you say that your operator is positive. And for causal operator, positivity is equivalent to passivity. Now, we know that this is a very important property because it has a physical interpretation, and also because it's central to analyze feedback system because of the passivity theorem that its property is preserved by negative feedback. And finally, this passivity property has a very close relationship to the gain that I was talking earlier, because if a plant is passive, then the feedback loop of the plant with identity will have small gain, the inverter. So there is this very close relationship between the gain property of an operator and the passivity property of an operator. Now, in that textbook, the property of passivity is really put side by side with the incremental corresponding property, which is the same property, but you replace the signals by increments of signals. And so now this incremental positivity property, you call that monotonicity. So monotonicity is the positivity of the inner product between the increments of the input signal and the increments of the corresponding output signal. But the passivity theorem is the same in the non-incremental and incremental form. And the relationship between gain and phase is also the same, that if the operator is monotone, then the inverse of this operator plus identity is contractive. Again, contraction in the sense of, in the operator theoretic sense, that the incremental gain of that operator is smaller than 1. So you will appreciate that incremental and non-incremental, even though the fundamental properties of passivity are the same, the two properties mean something different. So on the left, you have an example of a graph of a function that would be passive but not monotone, okay, because it has a region of negative slope, but it is passive because the graph is entirely in the first and the third quadrant. And on the right-hand side, you have something that is monotone but not passive. So the slope is always positive, but the mapping doesn't go to 0, and therefore it's not passive. So you could say that non-incremental passivity is a monotonicity property, but always with respect to the zero equilibrium trajectory. In contrast, passivity, the incremental form of passivity is between any two input signals. Okay. And it's quite striking to see that 60 years later, passivity, the non-incremental form of passivity, is very central to control, but you don't hear much of passivity elsewhere. And in contrast, this monotonicity, so the incremental form of passivity, is very widespread, in particular in optimization. And so this is an example of a recent textbook that uses this property of monotonicity at its core for large-scale algorithmic optimization. So now I'd like to say a few words about state space theory. So the state space theory, the reason why it's non-incremental mostly is that it is grounded in Lyapunov theory, and Lyapunov theory is a non-incremental concept, because Lyapunov theory, you compare the energy or the storage of a state, but always with respect to the zero states, to the minimal state of the storage. So the comparison between two is always with respect to the equilibrium, but it's not an incremental concept. And the consequence of that is that because Lyapunov theory is the foundation of passivity, dissipativity, the nonlinear, I mean, pretty much a very large part of nonlinear control theory, all those concepts are immediately non-incremental. And the consequence is that the central problem of all these textbooks is equilibrium stabilization, but it's not so easy to move from the design property of equilibrium stabilization to the question of robust performance analysis of a feedback system. Now, of course, this is not to say that incremental properties have not been studied in state space theory. In fact, over the last 2 decades, there has been a lot of work trying to go from the non-incremental concept and studying their incremental version. So the most important one perhaps is what I would call incremental Lyapunov stability, that is called contraction by Lohmiller and Slotting. And that plays now a very important role in the analysis of state space systems. But the same is true for incremental positivity and the notion of monotonicity that was first developed by Angeli and Sontag. But pay attention to the fact that this notion of monotonicity is not the same as the operator theoretic notion that I've discussed previously. And then there has been work on incremental dissipativity, and more recently, and I see that this will be the topic of the next webinar on incremental Port-Hamiltonian modeling. So there has been a lot of efforts to sort of generalize the non-incremental theory to an incremental theory, but with two important comments that I would like to make. First is that the monotonicity and contraction property that we talk in that context are always in the state space. So it is a contraction from if you think about the map that maps the initial condition to the solution, not about the map that maps the input to the output. And so it leads to the different notion of stability or monotonicity. And what I find most striking is that it's not easy at all to connect the incremental properties associated with the state space to the incremental properties associated to the input-output approach. Okay. So if we go back to our two very simple examples, we have beautiful illustration of that phenomenon. So if we take a nonlinear PI controller like a Clegg integrator of the Higgs integrator, any form of this hybrid system modification of classical integrator, usually all those models are passive. Okay, and you would expect that. I think that a nonlinear PI controller should be passive. But I would argue that I would also expect that a nonlinear PI controller would be incrementally passive. And well, certainly, if a nonlinear PI controller had that property, we could say a lot more about the robust performance of this particular feedback system. We could pretty much apply linear theory for the analysis. But the striking fact is that most of the state space models of these nonlinear PI controllers, we don't expect them to be incrementally passive. In fact, to most of them, it's an open question whether they lead to an incrementally passive input-output operator. So isn't that striking that for such a simple example of state space model, we can say a lot of things about the passivity, but very little about the incremental passivity. And the same thing about this memristive circuit that I have mentioned in the introduction. Again, you have an extremely simple lagged resistor. It's very easy to show its passivity. But in fact, in this case, we can show that it is not incrementally passive. So we can do that by constructing pairs of inputs and computing the inner product with the corresponding outputs and showing that this inner product is not positive. But from a biological viewpoint, this model certainly should be incrementally passive in the sense that for a biologist or a neurologist, this is a prototype of a current source that has positive conductance. And positive conductance is just a physical translation of being incrementally passive, of having this positivity property incrementally. And but the fact is that this state space model is not incrementally passive as an input-output operator, and that this is, I've come to regard this as a main obstacle to the robust performance analysis of neuromorphic electrical circuits. So the summary is that I think that there are very puzzling gaps between incremental input properties as they were defined in the original theory of Zames and de Zool and Mediafagar, and the incremental properties that we can derive from state space representation. And fundamentally, we lack a proper bridge between the two that would either be an incremental dissipativity theory or an incremental KYP lemma. So in the linear case, we go from the internal properties to the external properties very easily, thanks to concepts such as the KYP lemma, but we lack such tools in the nonlinear case for the incremental properties. And once again, I come to regard this as a main obstacle to robust analysis of nonlinear feedback systems. And I think that what is striking is that this gap is not just a mathematical gap, it's really affecting the most elementary examples of nonlinear control systems, as the two examples that I have chosen for this presentation. So at this point, when I came to realize this not so long ago, maybe about 4 years ago, I was really stuck, and the question, of course, for me was how big is the gap, and how important is this gap? Is this, and I didn't really know how to measure that gap, how to know that the lack of incremental passivity of these two examples is an artifact or is something more important, or. And the answer to that question came from the PhD of Tom. So I remember the day where Tom came to my office and said, have you heard of this graphical tool called the scale relative graph to describe the input-output properties of an operator? And I said, no, never heard of it. And then, yeah, we start looking at, in fact, that tool was introduced not so long ago. It was introduced in a paper in 2021. And but the conclusion that arises from the thesis of Tom is that the scale relative graph of an input-output operator is really the generalization of the Nyquist curve of a transfer function. So it provides a graphical tool for incremental input-output analysis. And so this talk will not be about the scale relative graph. That would require another talk. But the concept is easy enough for me to give the definition and then to show how I've been using that concept. So the definition is really simply the idea of associating a phase to a pair of signals, and that's something that is quite classical. We know the relation between the inner product and the phase. But then to map that information in the complex plane in a sort of very natural way, it is somewhat humbling to see that this tool has not been introduced in control and has not been introduced 40 years ago, but instead has been introduced recently in optimization to facilitate the convergence analysis of optimization algorithm. But what you recognize here is a complex number that you associate to any pairs of signals U1 and U2. And the modulus of that number is nothing but the incremental gain, as defined in Zame's PhD, and the phase is just the inner product of this difference. So in the linear case, that's exactly how you generate the Nyquist curve of a plant. And indeed, all the intuition that you have about the Nyquist plot of transfer function carries over this scale relative graph of nonlinear operators. So the monotonicity that I've been talking about, the incremental passivity, translates into the scale relative graph being in the right half plane, very much like the Nyquist curve of a positive real transfer function. And the gain property translates in being inside the disk. And so all these graphical rules that we have used in the context of classical control translate into those graphical representation of operators. It's quite an interesting development, I think, but for another talk. Now, what I want to show is that if you take this nonlinear integrator that I've been discussing in my example, and if you generate numerically this scale relative graph, so for you generate two pairs of input signals, you compute the outputs through by simulating this switching integrator, and then you compute the phase and magnitude, and you plot one point, and you do that for many pairs of trajectories. And okay, this was the master thesis of a student, Zixing1, but you see that all the points that he has generated numerically from this integrator system appear to be in the right half plane. And this suggests that, yes, this system should be incrementally passive as an input-output operator. And that's very reassuring that to think that this, because it would mean that we could still think of nonlinear integrators as being incrementally passive. But as I said earlier, to the best of my knowledge, it is an open question whether the input-output operator of that system is incrementally passive. And I think there are good reasons why it is probably not. But you see that if you just try reasonably to generate to generate points of the scale relative graph from numerical computation, it's always in the right half plane. And this is the scale relative graph also numerically generated for these potassium currents. And yeah, I love this picture because it shows that there are a few points, a few data points that are in the left. So here you have a numerical proof that this state space model does not lead to an incrementally passive operator. And yet you see that most of the points are in the right half plane, and that it really looks like those few points in the left half plane are sort of like of an artifact. Now, once I saw this, I sort of became really puzzled of why is it so? Why is it that the simplest model of a nonlinear resistor with memory should not be incrementally passive? What is there any physical reason for that or biological reason for that? Because we talk about here a biological model. And I went back to the original paper of Hodgkin and Huxley and sort of revisited the way they derived this state space model. And it's quite striking that, you know, the reason why Hodgkin and Huxley got a Nobel Prize for this paper is because they designed an experiment that made it possible to identify the input-output mapping of these current sources. And what they did for the potassium current is to plot, what we see here is just a family of step responses of that current source of different amplitudes. So you apply step changes of different amplitude and you measure the corresponding input current. And what you see indeed is that you have essentially a sort of a first order lag, but a very, very simple type of responses. But of course, the response is amplitude dependent. And it is from those data that they just do a parameter fit to obtain the state space model that I have been discussing earlier. So I find it of course, this family of input-output responses are perfectly monotone, are perfectly incrementally passive. So there is nothing from the experimental data that would justify that this input-output operator is not monotone or incrementally passive. It is only the state space model that has been fitted to those experimental data that has lost the incremental passivity property, with the consequence that nowadays we are stuck when we want to analyze those circuits. And I think this is something, to me, this is something very important, because it means that somehow when we do the data fit of starting from experiment and starting from experimental data, it is very likely that even if the physical property was there, it has not been retained in the state space model, because of course, Hodgkin and Huxley never paid attention to retaining that property. And this is sort of an observation that pushed me to what I will present next in the last part of my talk. And this is the work that I've been doing with Henk. So of course, it was a very natural question when Henk arrived in the lab and to ask someone who had just completed a dissertation on data-driven system identification to tell him, okay, here I have a perfect example of a nonlinear problem, which is data-driven. I'm giving you 10 input-output trajectories of the system. And I wish to build a model, an input-output model of those of this device. And of course, I would like to have reasonable fitting properties. So I would like my data my model to fit the data. But I also would like my model to, I don't know whether you see this bar, very annoying, but I hope
no, there is no bar.
Oh, there is no bar. So good, because I have, and I don't see the entire slide, but it's good if you see the entire slide. So the data fitting, but on top of that, I would like to, in this case, to preserve the monotonicity of the data. And I think that based on physical argument, this operator should be monotone or incrementally passive. What can we say about this? How do we start this problem? And well, clearly, if I start from a nonlinear state space model, I have no clue how to address this question. But I think that the solution that Henk developed is very appealing and to me extremely promising. So I think that the important connection was to connect that question to a very, very classical question, which is the problem of linear regression and regularized least square for linear regression. So when we do linear regression, we can think of it that we have an input space that is just a finite number of vector data, and likewise for the output space. So, and we want a linear map between the input and the output. So in this case, it's just a matrix. And so we want to fit a model, a linear model. Is just, we want to find a matrix that minimizes this quadratic cost function. And this quadratic cost function has one term that minimizes the residual error, so that this term is for the data fits, but it also has a term that is what we call the regularization term. And the regularization term is the purpose of that term is not to overfit the data. And you want to sort of balance this trade-off between the data fit and the system properties with a regularization parameter. And typically in least square, you penalize just the matrix norm of that operator. So clearly, I mean, this is an example that we studied in our bachelor degree. And we know that if we push the regularization parameter, of course, we penalize the norm of that operator. So obviously, we will end up with a norm with a small norm. And so clearly, this is one example where you can, by playing with the regularization, you can sort of find a good trade-off where you still have a good data fit, but you also control the norm, that is the gain of this linear operator. And to me, what is, I hadn't thought, I must say, until working with Henk, as input-output, these incremental input properties as regularization properties of an operator. But I think that's exactly the right way to think about them. And now you could say, well, this is feasible because this is finite dimensional and this is just least square. But what if I have a signal space here, a signal space, typically the signal space is L2, and then I want to identify a nonlinear operator in those signal space. This sounds completely daunting and intractable. And indeed, it is intractable if your signal space is L2. But it is very well known in machine learning and in statistics that you do have a class of signal spaces where this problem is tractable. And it's not enough to have a Hilbert space like L2, but you need a Hilbert space with a so-called reproducing kernel property. And then you have a most important theorem of the theory of reproducing kernel Hilbert space, that the problem that I've just talked about is tractable and is in fact has a finite dimensional solution, even if your operator is in infinite dimensional space, provided that you have this extra property for the signal space. I have no time to talk about reproducing kernel properties. So if you know what it is, I don't need to explain. If you don't know what it is, I will not use this seminar to explain what it is, but you will just accept that it is some extra property on top of being a Hilbert space that creates that magic. Now, perhaps one way to think about reproducing kernels is to see whether they have been used in system theory. And indeed, in the last 10 years, there has been a lot of use of the reproducing kernel property in linear system identification. And in fact, Lennart Jung is claiming that this is a paradigm shift in system identification. And this is an example where instead of parameter, so here you look for an impulse response. You characterize you identify an impulse response, and the classical method of system identification is to parameterize this impulse response with the coefficients of an ARMA model. But here instead, you have a non-parametric method. You only impose to your impulse response to belong to a space of functions with the reproducing kernel property. That has been very successful in linear system identification. What we want to do here is sort of a nonlinear version of that, because we want to be able to identify nonlinear operators. And so we don't identify a function like the impulse response, but we identify an operator. And the main result that I will not even read in this seminar for the sake of time, but that just expresses what you hope that it would work. And it's just saying that indeed, if you optimize your least square, regularized least square costs in that space of operators that have the reproducing kernel property, then indeed the problem remains tractable and you have an algorithmic solution. So you have a way to use the regularization term to play with this regularization parameter and to enforce a small incremental gain for the operator. So this is an example showing that the problem that I've posed here, that I'm giving a set of input-output trajectories, and I'm asking to identify a nonlinear model that fits those input-output trajectories, and at the same time, in this case, satisfies small gain incremental condition, that problem is tractable in reproducing kernel Hilbert space. And this is an example of the paper that we wrote where, we have just applied this method to the data of Hodgkin-Huxley, and not surprisingly, could, with some choices for the kernel that are not important to discuss, I think, with an extremely small regularization parameters, you satisfied a small gain condition. Now, the property that I wanted to enforce with, in that example, was not a small gain, it was a monotonicity property. So the question is, how do you go from enforcing a gain to enforcing a monotonicity property? Well, you use the relation between passivity and small gain. So you use the so-called scattering transformation, and you reconvert your problem as the problem of doing a data fitting under a small gain condition. So using this scattering transformation, you can generalize the problem that I've talked about, where your constraint is not just a small gain condition, but is any input-output incremental property that can be written as an integral quadratic constraint. And I think that we are at the very beginning of those results, but I think to me it's opening an entirely new world to derived nonlinear models that not only fit a set of input-output trajectories, but at the same time satisfies a number of incremental input-output properties. And so we could apply this to the potassium currents if we want to analyze those neuromorphic circuits. We could apply this to the Higgs integrator if we want to design controller that have specific incremental input-output properties. But somehow we see that we can use a very successful framework in machine learning to develop an algorithmic framework for the robust performance analysis of nonlinear feedback system. I like to conclude with an outlook and just summarize the main point of this seminar. And so the first point that I've tried to communicate is that because nonlinear state space theory is grounded in the Lyapunov theory, most of the concepts of nonlinear state space theory textbooks are non-incremental. And that even when you try to work out the incremental version of those concepts, you don't end up with properties that can be easily related to the input-output incremental properties that we need to apply the feedback system analysis of ZAMES. In short, there is no KYP lemma for incremental analysis of nonlinear system, and this is a very, very important limitation, I think, of state space modeling. And this limitation affects some of the simplest model of circuit theory and nonlinear actuators, and I've given you two examples. Now, the positive side of it is that I think that the time is ripe to have another path at input-output theory, because the reason why input-output theory was abandoned in the late 70s is because it was non-algorithmic, because those abstract operators in L2 didn't lead to any concrete design methodology. But if we now revisit the theory with all the tools of machine learning that have developed this very solid framework of reproducing kernel Hilbert space, we have a completely new angle of attack where we can reconsider those classical tools. And I think it will be extremely handy to handle applications of the type that I have mentioned. So the way I would apply this to this example is that you could generate a family of input-output trajectories with the state space model that you like to describe this device. I would then extract an input-output operator with the additional, let's say, monotonicity property, because I want my nonlinear PI control to be monotone. And then I would go on with the design and the design methodology that, thanks to the scale relative graph, to this graphical technique, would be very, very classical and very close to what we do in linear control. One thing that I haven't mentioned is that this approach in the context of electrical circuits also opens a door to analyze systems that are not equilibrium systems. And so the way I define sort of a framework to analyze spiking systems is just the feedback interconnection, what I would call the mixed feedback interconnections of monotone operators. And again, once we have such a structure, we can make the analysis of these feedback systems very algorithmic, even though the solutions of those feedback systems are not equilibrium solutions, but can have limit cycles and switches and whatnot. So perhaps my concluding slide is that research goes into circle, and that the very start of feedback system analysis was an input-output theory of incremental properties. For the reason that I've explained, we went from input-output to state space, but in state space theory, the theory became very non-incremental. And then through this non-incremental theory, the interest for incremental properties like incremental stability, incremental passivity, redeveloped, but from the state space. And now we are sort of led back to return to perhaps input-output representation that are an alternative to state space representation. And I would like to conclude with the fact that it's not to say that we should reject state space modeling. State space modeling is extremely useful, for instance, to obtain a model from the physics or to simulate a model. But the main reason why we like state space in linear theory is because it provides an algorithmic theory. And that property is lost in the nonlinear world. So far, state space models have not led to an algorithmic theory of nonlinear control. And perhaps that we can look around and see that in machine learning and optimization, these alternative input-output representation are as concrete as state space models in terms of their algorithmic properties, and perhaps will allow further progress in developing an algorithmic theory of nonlinear feedback systems. And I will conclude with this. Thank you in advance for your questions.
Thank you, Rodolphe, for a very inspiring talk and also insightful. There are a few questions from the audience. So maybe I would like to invite Eduardo Aranda from Mexico to tell your questions. So Eduardo, if you'd like to turn on your microphone and ask.
Thank you, Bayu. I do not like to put my camera on, but I'd like to ask Rodolphe. For me, I am reluctant to the input-output approach. I cannot see how do you tackle or to address to the internal dynamics of a system. Is it possible that you solve very interesting problem from the input output point of view, but internally, system is exploding.
Mm-hmm. Yeah, I guess this has to do with the minimality, but I think if you think about circuits, you know, the way we think about electrical circuits is that we interconnect possibly many elements, but each of these elements is very simple, and very simple in this one way of expressing that simplicity is that there is no internal dynamics. If you think about this first order model that I've been discussing, whether this resistor with a lag or this PI control, I don't think that you can think of those elements as having internal dynamics that explodes, while the input-output behavior is. So I think that for those type of elements, and this can be further characterized and needs to be further characterized, but I think you will agree with me that for those simple elements, the internal behavior can be completely understood from the external behavior. In fact, systems that have that property have a name, and they are called relaxation systems in the theory of Willems, and this is something that we are very interested at the moment to exactly characterize those systems that for which the external description is sort of equivalent to the internal description.
It comes to my mind a very simple example: the non-holonomic integrator, or for that sake, the unicycle robot, and you can control precisely, for instance, the X and Y coordinates, and yet you cannot do anything with the orientation angle. So it is in that sense that I wonder how can you tackle that.
Yeah, of course, it all depends on what we mean by the outputs, and
yes.
But I think that when we think about physical systems, and in particular electrical circuits, the input outputs, it's not something that we choose. So we don't invent the output. In fact, what we call the input and the outputs are always paired variables, for instance, current and voltages, or force and velocity. And this is sort of imposed by physics. And in fact, whether we call the current the input and the voltage the output, or vice versa, doesn't matter. So it's really the relation between current and voltage that we want to capture. Now, I agree that, and it's good that the example that you point out is from mechanics, where in mechanics, these non-holonomic systems is an example where, you know, again, in simple mechanical systems, it's easy to do this pairing of force and velocity or generalized coordinates. But once you have these non-holonomic constraints, you are in a situation that is slightly more complicated, right? So I think you are perfectly right that it is a very important comment that you are making, that when we describe a system from its terminals, from its external ports, we should pay attention to whether anything can go wrong inside.
Yeah. I do not want to abuse of your time. Thank you very much, and we hope to see you again in Mexico very soon.
Yeah, thank you, Eduardo, for questions. And we do have any interesting questions also from Nima. So Nima, if you like to turn on your microphone.
Okay, can you hear me?
Yeah.
Okay, thank you, Rodolphe, for the, as usual, very interesting talk. I typed my question in the chat, so I'm going to just read out aloud from it. So you mentioned the gap between the properties you see in the stasis space models versus what you see in experimental observations. And this gap, could it be partly due to the fact that, theoretically, passivity is defined for arbitrary inputs, but maybe not all those inputs are relevant in the actual physical biological system?
Yeah, well, I think it's a very good point. So again, it could be that we use a state space model to represent an input-output relation in a certain context, but then the state space model sort of allows to describe input-output trajectories that we haven't seen in the physical device and that perhaps are not even physical. I don't think it's the case for this potassium current. And so if I go back to this scale relative graph, I think it's quite insightful that, you know, if you sort of, here all the inputs and outputs are generated sort of naively. So with input and current as you would expect them in the biological situation. And so you still see a few of those data points that I think that there is really no reason why a state space model that you identify through data fitting would need to retain any input-output property of the operator. There is nothing that enforces that in data fitting. And that is true even in linear regression. And so that's why very early on, when we do linear regression, we have developed the concept of regularized least square, because just data fitting, there is no reason why data fitting should enforce any system property. So I don't think it just has to do with whether the state space model is physical or not physical. I think it's deeper than that. It's the fact that the state space model, and we know that already in linear system theory, that you would never identify a state space model if you want to retain input-output properties without enforcing at the same time, let's say, a passivity property, because otherwise you know that you will not, there is no reason why you would retain it. So we can still do system identification in the linear theory thanks to the KYP lemma, because we can sort of express those input-output properties in the state space. But there is no obvious way to do that in a nonlinear case. Does that answer your question?
Yeah, yes. In fact, I was intrigued by the same figure that you are now showing on the screen. These are generated by experimental or numerical?
Numerical.
Numerical.
Yeah.
Right. So indeed, for instance,
but not from real inputs. So
right. So for instance, the ones that goes on the left could be those maybe that I would call not realistically or physically significant inputs.
Yeah, but I don't think that there is any reason for that.
Mm-hmm.
For what I just explained. I think it's the result of, it's an artifact of the data fit, and the fact that there is nothing in the data fit that enforces the fact that you don't want points in the left-hand plane.
Okay, thank you.
Okay, so thank you, Nima, for the questions. There is also a comment by Andrea that he has to teach. So he said thank you to you, Rodolfo. So maybe one final questions from my side, because I don't see there are other questions in the chat. You briefly mentioned earlier about the behavioral framework, that input-output is just an artifact. We should see them as a pair of signals. So looking into your result using the reproducible kernel, or the one that you're working with, Heng, are you also looking into the fitting, but not instead of input-output, but more on the behavioral framework, where the input and output is just considered as a signal, if you know what I mean?
We haven't done that, but I think it just makes no difference. So if you prefer the behavioral framework rather than the input-output framework, I think all what I've said will remain. So indeed, this using developing relations in reproducing kernel Hilbert space as opposed to mappings or operators is I don't think it's a big
I see.
Big difference.
Okay, so thank you again, Rodolfo, for a very nice talk. And due to the time, I think I would like to close this webinar sessions for today. And I would like to remind everyone that we will have the next talk by Professor Arjan van der Schaft on the Wednesday, 15th of March. So thank you again, everyone, for coming, and also Rodolfo for a very nice talk.
Can I ask one question? Excuse
me.
Oh,
yes. Oh, okay. So one question. Go ahead.
Like Rodolphe Sepulchre to discuss shortly how this theory which is actually input-output theory, relates to the Volterra series model, which is also considered a basic input-output model. What is the relation between these concepts and the concepts built in the Volterra series model?
Yeah, I think that this is a very good question. And I haven't really looked in details at Volterra series. But I think that the idea of Volterra series is the idea that, okay, there is a certain class of operators, so the convolution, the linear time invariant operator that we can represent with convolution. How much can we push, how much can we generalize the idea of convolution to capture nonlinear operators? So I think that those theories are very much driven by the convolution idea. And,
right.
and I'm not saying that, and so far in what I've presented, I have not put any emphasis on convolution operators, whether linear or nonlinear. But I think that those questions certainly come into play once you talk about a question that I haven't talked about, which is, okay, suppose that I have this algorithmic kernel representation of my operator and that I like it because it's very practical algorithmically. It's still a very pertinent question to say, how do I derive a state space realization of these kernel operators? And there, I think that it's completely open, but it's a very interesting research question to see how are we going to sort of constrain the choice of the kernel in such a way that those operators also have a state space representation. But that is a separate question that I haven't even touched upon in this talk.
Okay, thank you.
Okay, thank you. So I think with that, we are going to definitely close the session. Thank you everyone for joining.
You have another question.
Oh, we do have another questions. Rodolphe, do you have time?
Sure, with pleasure.
Okay, Claudia, can you tell us the questions?
No, it was not me. It was Kamen Pereb. He was raising his hand.
Oh yeah, Kamen has asked just now. So he has just asked.
I cannot turn on my video actually.
Okay, so then with that, I would like to conclude the webinar series. And again, thank you everyone for coming. See you next time. Have a nice evening, afternoon.
Thank you.
All right.
Thank
Bye-bye.
you, Rodolphe.
Thank you very much.
Thank you.
See you soon, guys.